a great pleasure. For our last talk, we have Francisco Reyes from Universidad de Santiago de Chile. Please.
Thank you. Thank you, everyone. First of all, I would like to say thanks to the organizers for giving me the chance to give this talk. So this work is based on this article here, and it was a collaboration with Cristian Lara and Miguel Pino, my PhD advisor. So the aim of this talk is to show how through the suitable choice of boundary conditions for the gravitational field on ADS-3, such that deforms the Brown-Henault ones, it is possible to find a connection with an equivalence between the asymptotic dynamics of ADS-3 and a family of nonlinear partial differential equations known as the Harry-Dim hierarchy, which is a 1 plus 1 dimensional integrable system. So let me start motivating with general relativity in 3 dimensions. From a holographic perspective, general relativity in 3 dimensions has been a fruitful scenario to study some aspects of the gravitational field. In particular, let me focus on ADS-3. This theory is trivial from the bulk perspective because every solution of the Einstein equation is locally ADS, and therefore it does not propagate degrees of freedom. Despite this, J.D. Brown and Mark Henault, in a preliminary work on holography, show that through the suitable choice of boundary conditions, it is possible to find, as the asymptotic symmetry algebra, 2 copies of the Virasoro algebra with a possible central charge known as the Brown-Henault central charge. In this context, the theory admits a black hole, the VDZ1, and Cousser, Henault, and Mandril show that through the suitable choice of boundary conditions, the theory exhibits boundary degrees of freedom. So it is important, to define suitable boundary conditions. First, because they let us find asymptotic symmetries, which are a family of gauge transformations that preserve the form of the boundary conditions, and they can change the state of the system. They should define a well-defined action principle, and they must allow solutions of physical relevance, such as black holes. Some examples are the soft hair proposed by Haugenberg and Strominger as a family of asymptotic symmetries that appear in the near horizon of the black hole, and where the boundary conditions of ADS have played a role to understanding the soft hair. And in a different context, Pérez Tempo and Troncoso, in a similar work, showed that through the suitable choice of boundary conditions, the theory, the asymptotic dynamic of ADS-3 has an equivalence with the KDB hierarchy, and in another way, Cárdenas, Correa, Lara, and Pino showed with a more general choice of boundary conditions that the theory is equivalent to the AKNS system, which is a more general integrable system. So, is this our motivation? And we are trying to exploit this connection between general relativity and integrable systems. So, let me introduce some aspects of integrable systems. Many of equations that govern the nature are nonlinear partial differential equations. Much of them don't have analytical solutions, but some of them that do, and they are named integrable systems. Some examples are the KDB equation, nonlinear Schrödinger, AKNS, as I mentioned, on the DIM equation. So some of these integrable systems share some properties. In particular, I will illustrate them through an example, through the DIM equation, which is given here, where L are the fields, which depends on time and a spatial coordinate. And one property is that it is a bi-Hamiltonian system, which means that you can construct this equation through an operator acting on a quantity which can be written as a variational derivative of something. And at the same time, it can be written as another operator acting on another quantity, where for the DIM case, the operators are given as here, and the quantities H are these. Another property is that the operators define a Poisson bracket, and they are named bi-Hamiltonian since they satisfy a compatibility condition, which means the composition of them, the sum, define a new Poisson bracket. And the operators satisfies our recurrence as here, and then we can construct an infinite amount of these quantities, and we can show by means of this relation that they Poisson commute, and they are in involution, and they are conserved charges of the system. And another property is that some integrable systems can be written as a zero curvature formulation, and this is the link that we will use to connect with general relativity. So let me comment about general relativity in ADS3. The action of ADS3 can be written as two copies of the Chern-Simons action, where A are the gauge fields spanned in SL2R algebra, on case level, where L is the ADS radius, on G the Newton constant in 3 dimensions. If we vary the action, we will find the Einstein equations, which corresponds a zero curvature equation, where, as I mentioned, is the point where we link with integrable systems. And in Hamiltonian formalism, the Chern-Simons action should be supplemented with a boundary term in order to ensure that the action vanishes in shell. So we can see that it is important to define the behavior of the fields at the boundary, right? So before imposing boundary conditions, we can choose the fields such that they satisfy the following gauge transformation, where B is a gauge parameter. I'm sorry, we are here working on with polar coordinates. Yeah. So B is the gauge parameter which encodes all the radial dependence of the fields. So the gauge fields can be written as follows, and we will choose the spatial component as here, such that it ensures the asymptotically ADS behavior fields, and the most general choice of the temporal counterpart that preserves the above is given as here, where L are the capital, calligraphic L are the fields, the dynamical fields of the theory at the boundary, and mu are functions, are functions that must be fixed. And L are the generators of SL2R algebra. So if we solve the zero curvature equation at the boundary, representing with the fields, the fields that I showed before, we will arrive here. And they can be written, the equation of motion can be written as here, where D and E are the operators that I showed in the previous section. And C is just our dry definition of the Brown-Henon central charge to avoid these factors, 24 pi. It's just it. Now, inspired in a work of Ablowitz, Cobb, Nigel, and Sear, we will introduce a polynomial ansatz for the quantities mu. It is not a series expansion, it's just a sum in negative integer powers of c, as here. And if we introduce this mu on the equations of motion, and solving order by order in C, we will find this set of equations that must be fulfilled. The first one is a dynamical equation. The second and third are conditions for mu0 and mu1 respectively. And the last one is a recursion relation. We have here the values that they must have. And this equation is solved with this condition. So mu must be the variational derivative of these quantities, which belongs to the equation. So in general, we have this form for the functions mu, and if we replace the mu on the dynamical equation for every capital N, yes, for every value of capital N, we will find different equations which belongs to the Hardy-Dim hierarchy. So now we are in position to study the consistency of the boundary conditions. First, we can see that the boundary term integrates in order that if we introduce the boundary conditions and the mu's, we will find that the boundary condition is proportional to the conserved quantities of the integrable system. Regarding the asymptotic charges, we have these charges which are proportional to the conserved quantities of the Dim equation, where m here is a number, an integer, not necessarily equal to n, to capital N, as in the ansatz. And by means of this equation, we can find the asymptotic symmetry algebra, which reproduce the behavior of the conserved quantities of the integrable system. I mean, it is abelian and infinite dimensional. And regarding the solutions, we can find the metric by means of this equation. And for the simplest solution of the hierarchy, that is L equal constant but greater than 0, and therefore mu is equal to a constant because it depends on L and its derivatives, we can find this metric, and with defining the radial coordinate, we can write it in Churchill-like coordinates, and therefore we can construct the ADM formalism of the metric, where the lapse and shift functions depends on the functions mu. Okay. So the horizon is given as here, and from the conserved charges we can identify the mass on the angular momentum. On the space, the solution spectrum is given as here, where we notice that the extremality is not admitted because the solution doesn't admit these values. On by means of the Euclidean counterpart of the metric, we can construct the thermodynamic properties here. Yes, and we have the temperature on the angular velocity of the horizon in order to regularize the metric. Yeah, and the Euclidean action by means of the Reyes table analysis. The boundary term reads as here, and the entropy respects the Bekenstein-Hauke law. Yeah. So, as a summary, we have constructed the Dim boundary conditions, exploiting the behavior of the Lagrange multipliers represented by mu. They allowed a well-defined action principle. They render a finite and non-vanishing charges. The asymptotic symmetry algebra is finite dimensional and abelian. on black hole configurations are allowed, but not its extremality. And further work can be made, for example, to explore non-trivial solutions of the dim equation. It has periodical but not explicit solution, and more general gauge theories. It is possible to extend this duality between gravity and integrable systems in more general gauge theories in higher dimensions or with degrees of freedom. That's something that we are trying to study now. So, thank you for your attention.
Thank you for the talk. Just so this last comment, so you did it for ADS3, but this that you can write three-dimensional gravity as Chern-Simons is also true for flat and de Sitter with other gauge groups, I think. Do you also look at that, or does something go wrong? Or?
I'm sorry.
So, do you use some other fact about ADS3 then that you can write it as this Chern-Simons version? Because I think you can also write gravity in flat in 3 dimensions as Chern-Simons or in de Sitter.
I think I understand why I'm working in Chern-Simons.
No. I was asking because you can, you can write also gravity in flat space and in de Sitter as Chern-Simons. So I was wondering if the same goes through there. The same, if you can find an analogy to.
Oh, okay. Yeah. Maybe in de Sitter it could be a problem because it doesn't have a boundary.
Okay.
In flat spaces, we would like to do this work. Yes,
okay.
Yes. I think it is possible to.
Super naive question because I'm not an expert at all, but formulating gravity in 3D at Chern-Simons, so you have the solutions, are there any candidates for like microstate solutions in an higher dimensional supergravity, stuff like that? People would construct those various solutions. Some of them are candidates for microstates or black holes. In that case, does the Chern-Simons formulation shed any lights on building microstates for those BDs-like black holes?
I don't know.
Maybe different way of the question is that any hope to classify solutions, that would satisfy some boundary conditions
from the integrable system.
Yeah.
Maybe it is possible. We try to do that, but the integrable system, it is not possible to construct a systematic way to find solutions. And most of them are not periodic, and it is a criteria that we have to consider at the moment to construct boundary conditions. They must be periodic. But we are studying. We're trying to study some other solutions, periodical solutions, but they are not explicit. You can solve them, but numerically. But yes, the big problem of integrable system is that they can be systematically construct the solutions.
So I have a question about your, for further work. So you said that you will also consider more general gauge theory. So is there an example of a gauge theory that you are looking forward to consider in the future?
Oh yes, because at first we were we start considering a general gauge theory, but we stopped and we thought that it's wise starting with adding a degree of freedom, 1 degree of freedom, a scalar field minimally coupled, to see if it is possible to find an integrable system. First, we have to work in metric formulation, because if we add if we add a gauge, a scalar field, maybe we can write it we can write it in Chern-Simons, Chern-Simons formulation, but the choices of the potential is unique. There is an article of Hinault, Troncoso, and Zanelli, maybe, which demonstrate that there is a suitable and a particular choice of the potential, the self-interacting potential. And if we want to generalize this construction, we would like to have a more general potential.
Okay, thank you.
Okay, let's thank the speaker again. And next is coffee.